In this lecture, let us talk about double sideband amplitude modulation with carrier. Okay, therefore, amplitude modulation in practice is typically referring to this situation, double sideband amplitude modulation with carrier, and not the suppressed carrier situation. Okay, that we have discussed so far. So the suppressed carrier situation was used in earlier days, typically for transmitting data signals. Okay, for voice signals, AM with carrier is one of the most commonly used form of amplitude modulation. So basically what we are saying is that in this case your transmitted signal will contain the part that we have transmitted earlier, and we also putting a carrier component. So it looks something like this. Your modulated signal x of t is equal to already we have what you call a times m of t cos omega ct. What is this? This is your DSB SC in addition with a times cos of omega ct. You are transmitting the carrier with the DSB SC. If you rearrange this, then a you can take outside 1 plus m of t times cos of omega ct. Okay, so this let me define as E of t, envelope of the signal. Therefore, E of t times cos of omega ct. Okay, as you can see, the second term, this one is precisely the same term that we had earlier in the case of DSBSC. But here we are also adding what? The carrier, okay, which is a times cos omega ct, right? So AM with carrier, that means DSBSC with the carrier. So there is a carrier component specifically introduced along with the rest of the modulated signal in order to produce the final modulated signal x of t. So E of t times cos of omega ct, where E of t is defined as E of t is equal to a times 1 plus m of t. Now let us look at the time domain behavior of this waveform. It can be made to have very interesting property under certain condition. That is, if m of t, magnitude of m of t is less than 1. Okay, for example, if I ensure the magnitude of m of t is always less than 1, then what about this 1 plus m of t? This one? This 1 plus m of, I mean, when I say m of t is less than 1, that means my m of t is always lying between minus 1 and plus 1. After all, m of t is a message signal, right? M of t is a message signal, and when I say message signal, that means what? It is a voltage signal. Like you take your speech signal and it is oscillating between, let's say, plus 1 volt and then minus 1 volt. Okay, that's what we mean by m of t, mod of m of t is less than 1. Okay, so I do the scaling in the message waveform in such a manner that instantaneous amplitude never exceeds plus 1 and minus 1. That's what we mean by mod of m of t is less than 1. Okay, it always lies between minus 1 and plus 1. Every message will have some limits in which it lies. I can scale it up or down so that this condition m of t is less than 1 is satisfied. So in such a case, there is a very interesting property, that is the entity E of t, this E of t will always be a positive quantity. Why is it always positive quantity? Because 1 plus m of t, and this m of t is always less than 1. Therefore, 1 plus a less than quantity, mod of less than quantity, this is always positive. Okay, for example, still if you want to understand very clearly, let's take your a sine wave like this, and this one is 0.5 and this one is minus 0.5 volt, peak to peak volts. If you add with 1 volt, what will happen? A constant DC voltage is 1 volt. So this point becomes 1 plus 0.5, 1.5, and this point is minus 0.5, and here this point plus 1 volt, it becomes minus 0.5. Therefore, your signal looks like this. So this one is minus 0.5, I'm sorry. If you add these two guys, 1.5, okay, like this, then it starts from 1, it goes like this, if you add it. Therefore, here you have positive part and negative part in the original message signal m of t. Let's say this is my m of t. Now this is my constant 1 volt. If you add these two guys, then 1 plus m of t is always positive. It never exceeds minus, negative. Say this is a zero line, so it never comes down. In case if you take a waveform like this, let's take like this. This is plus 1 volt and this one is minus 1 volt. Now you take 1 volt like this. Now if you add these two, then what will happen? My waveform will like this. Okay, so this will be 2 volts and this will be 0 volt. It touches the 0 line. Okay, this is my m of t. M of t mod of m of t is equal to 1 in this case. I mean, maximum value it reaches is 1. That's what I mean by 1. Maximum value 1, this point is 1 and this point is minus 1 volt. In that case, if you add 1 volt, this step signal u of t, then positive half cycle reaches plus 2 volt and the negative half cycle reaches 0 volt. In case, if you take a waveform, let's say this is 2 cycles like this. Now let's say this is minus 1.2 volts plus 1.2 volts. Now add 1 volt with this guy. 1 volt. What will happen? If you add these two, let me compress. If you add these two, then okay, so it becomes 2.2 volts. And like this. Okay, so minus 0.2, so there is a 0 crossing line, so this point is 0 crossing. This is your x-axis and this is your 1 plus m of t. Because this point is minus 1.2 volts and this is 1 volts, if you add these two, 1 plus minus 1.2 is equal to minus 0.2 volts. That is why you are getting minus 1.2 volt there. Okay, and here this is plus 1.2 and in this point 1 volt, 1 plus 1.2 plus 1, it becomes 2.2 volts. So therefore it crosses as x-axis in 2 points, 0 crossing. If mod of m of t is less than 1, then the waveform is always positive. That's what we have seen in the first case. Okay, 1 plus m of t is always positive. Okay, if mod of m of t is always positive, then in such a case there is a very interesting property, that is the entity E of t. What is 1 plus m of t? E of t. E of t will be always a positive quantity. Okay, 1 plus m of t we defined E of t. So you can think of this as the envelope of the waveform. Okay, so envelope is always positive. So we can see E of t have a shape of m of t. Shape does not change, but it is lifted, that's it. Okay, so the point is E of t follows the shape of m of t. Okay, if you look at in the DSB, if you recall from DSB SE case, what is the envelope? Envelope is proportional to not m of t, it is proportional to mod of m of t, please recall. Okay, but here the envelope is proportional to m of t. Okay, shape does not change. Okay, if you recall your DSBSC, if it one second, if you recall DSBSC like this, a sine wave, if you do the modulation, then it will be like this, like this. This is my DSB SC waveform. So this negative portion becomes a positive portion here, right? So here it is negative, my message m of t is negative, but here message becomes positive. Therefore this is my envelope. So this is the envelope. So in DSBSC, envelope is equal to mod of m of t. But now what we are saying in amplitude modulation with carrier, you are making the condition. What is the condition? Your m of t is always less than 1. Then what is your 1 plus m of t? 1 plus m of t will never crosses the 0 axis. Therefore, instead of having the sine wave like this, now your sine wave becomes scaled up wave like this. Same shape, but it is not crossing 0 axis. So this is my E of t. Now E of t is what? E of t is multiplied by cosine omega ct. Look at the expression. Okay, so 1 plus m of t times cos omega ct, right? Now let me call this is E of t, and this E of t is multiplied by cos omega ct. Okay, so originally your m of t is like this. Let us say if you add 1, then it will be like this. It is shifted up, it is not crossing 0. Then you are multiplying this guy with the cos omega ct. Therefore now what happens? It is like this, like this. So this is your what? AM signal. AM signal with the carrier. Okay. So that is a difference between AM with carrier and without carrier. So let me draw very neatly like this. the same kind of envelope like this. So this is the waveform of your AM modulation. And what is this peak? And this one is 1 plus m of t, that we defined as E of t. So what we are saying is, you have a low frequency sine wave, this one, okay, low frequency sine wave. Just for the sake of illustration, okay, we never use sine wave as a modulating signal, as a message signal. Just for the sake of illustration, we are using a sine wave, okay. So don't think that we are going to use this sine wave as a message signal. So message signal is always your speech signal. For understanding purpose, I am taking the sinusoidal signal. So I have a low frequency sinusoidal here. Your modulated waveform will be cos omega ct. See, I am multiplying by cos omega ct. It is a very high frequency, like this. Let's say it is 1000 kilohertz. Multiply this and that. Once you do the multiplication of these two, then you will get like this. Okay. If mod of m of t is less than 1, you will see that this portion will never cross the time axis. So the shape is retained now. So therefore your envelope will be proportional to message signal m of t. So if it crosses the time axis, then we will have some problem. Okay. So because we lose the proportionality of the envelope, the envelope will be different. See, originally my message signal, let's say I will draw some for the illustration purpose. Let me put a big sine wave, big positive and small like this. Let me call this is my m of t. Now if I add 1, then it will be like this, 1 plus m of t. You multiply by cos omega ct, then what? How does it look like? It looks like like this. Let me stop at this point. So this is your, maybe I will choose some other color. No, this is my carrier component. No problem, right? Now the trace, look at the trace. This trace and this trace both are exactly same. Exactly in the same shape. So no problem, okay. In case if this guy crosses a zero time axis, then what will happen? Your modulate, let me take that case separately. So in case your signal looks like it crosses the time axis, then what happens? Your modulated signal will look like this, and this one will be like this. Now let me say this is my carrier. Now what is the trace? The trace will be like this. But what is the original trace? Original envelope like this. So this envelope and this envelope both are different now. So I cannot get back my original message signal. See here, my message signal m of t is taken as magnitude. This is my original message signal m of t. So there will be problem. Okay, so that is why we always look at m of t is less than 1. If m of t is not less than 1, then the typical condition is bad. So that is a typical time domain waveform of amplitude modulation with carrier, as against the waveform that we saw in the last lecture for amplitude modulation with suppressed carrier, I mean without carrier. Now let us look at in the frequency domain how it looks. To do that, let me say this is my m of t. You take Fourier transform, I will get a m of f. Okay, so let me define the message spectrum, the same our old friend like this. This is B and minus B 0 Hertz frequency, and this is m of f. Okay, so it has absolutely no reason for this particular shape. You can choose any shape as you like. Okay, now I want to show the carrier component a little more clearly. So let us see how it looks like. Now you can ask a question, why do we call, no, before that let me finish this. Suppose your message waveform has a spectrum, say minus B to plus B. This one is the Fourier transform, and it is non-zero between minus B to plus B and 0 afterwards. Mod of B greater than f. So what is the spectrum of the modulated signal? Do you remember? X of t is equal to A times 1 plus m of t times cos omega ct. Right? So what we said, this is your E of t cos omega ct. What is E of t? E of t is proportional to m of t. That's what we said till now, we argued. Okay, therefore this E of t, you take Fourier transform, I mean essentially you are taking the Fourier transform of m of t, and that is multiplied by cos omega ct. Okay, now still if you want to know very explicit relation for this, then you multiply inside A times cos omega ct plus A times m of t cos omega ct. This is my x of t. Now take Fourier transform on the both side. X of f is equal to A times pi of delta of omega or f minus fc plus A times pi times del of f plus fc. Okay, recall your Fourier transform. Del of t, if you take Fourier transform, you will get 1. Okay, and 1 if you take Fourier transform, you will get 2 pi del of omega. Okay, and by apply the frequency shifting property, e raised to j times omega naught t, then 2 pi del of omega minus omega naught. What is your cos omega ct? Cos omega ct is equal to e to the j omega ct plus e to the minus j omega ct whole divided by 2. If you take Fourier transform of this, 1 by 2 times 2 pi del of omega minus omega c plus 1 by 2 times 2 pi times del of omega plus omega c. Okay, 2 will get cancelled. So pi times del of omega minus omega c. Instead of omega, I am putting f minus fc. Okay, so that's how this expression has come. Plus, you take the Fourier transform of these two guys. So A times m of f minus fc plus A times m of f plus fc. So I have 4 components here. Now let us plot these 4 components in the frequency axis. Let's say this is my fc. At fc I have a delta function. Let me plot the delta function by A times pi, its strength is. And at minus fc I have one more delta impulse component, A times pi. Now at f equal to fc I have a frequency component with bandwidth of like this. This point is fc plus fb, this one is fc minus b, and this side also similarly likewise you have minus fc, this is plus b, and this one is minus fc what minus b. Okay, therefore this is around fc and this one is around f minus fc. So the same spectrum m of f is translated to plus fc and minus fc, and in addition to this there is a carrier component. Okay, carrier component, and here also a carrier component which was not there in the suppressed carrier modulation. Please remember, please recall. So the only way the spectrum of the AM signal differs from the spectrum of AM signal with the suppressed carrier is that the carrier component is not present, but here the carrier component is present. Okay, so that is the only difference between your double sideband with carrier and double sideband without carrier. Now you can ask a question, why do we call the earlier kind of signal as DSBSC? So basically this is a difference, no carrier component. So we have localized specific value of the carrier component. Okay, specific value of the carrier component along with the modulator signal. So this is a very important difference point between DSBSC and DSB with carrier. So the spectrum properties of this signal to some extent similar to that of DSBSP. Spectrum is same in the sense, if you want to find out the bandwidth, what is the bandwidth? This is my bandwidth. So what is the upper frequency? Fc plus b minus what is the lower frequency? Fc minus b. So this is equal to 2b. So in DSBSC also the bandwidth is 2b, and here also the bandwidth is 2b. So as you can notice, we have introduced actually a kind of inefficiency. What kind of inefficiency we have introduced here? Power. Okay, so we have introduced a kind of power inefficiency. That means not all the transmitted power contains useful information. See, this is my useful information. Okay, so this is my useful information. The shaded area is and my useful information. But what about this guy? It does not contain any useful information. What will you get from a carrier component? You don't get any information, right? After all, it is a sinusoidal signal. What will you do with the sinusoidal signal? If you give the sinusoidal signal to the speaker, what will you enjoy? Okay, nothing. Therefore, it doesn't contain any useful information. That means the carrier does not contain message wave information. That's what I am trying to say here. So, but the carrier is helpful to us in some other way in the receiver, which we have to still discuss. Okay, maybe in the next lecture we will see how this carrier makes our life very simple. If you don't have carrier, then the receiver will become very complex. That's what we discussed in the last lecture. But now with the carrier, your receiver will be very, very simple. We will discuss. Okay, so as far as the objective is concerned, it doesn't transmit the information. Okay, so that The purpose is not being solved the transmission of the carrier component, but it simplifies the your receiver complexity. Okay, so therefore in that sense the spectral component that we are transmitting will actually, this guy will actually waste of power from that point of view. Okay, therefore there is a kind of power inefficiency, because we are transmitting the carrier, so it leads to power inefficiency. Okay, that we have introduced by introducing the carrier component in the transmission process. Now you can ask a question, why should we do that? As I said, it simplifies the receiver structure. If you remember, in the DSBSE case, we are doing that passing through a low pass filter. We remove the carrier frequency component which we had. Okay, so even though then why are we anyway at the end we are not going to use the carrier component. Okay, if you recall from the previous lecture that we filtered out by the low pass filter. Okay, that is high frequency component. So then still why do we need? Because it simplifies the receiver structure. Okay, so maybe I'll put one more time this diagram. You have the component like this. Even though you have some value here, some value, but at particular point that value will be 0. Why? Because this is density component. Okay, spectrum density, amplitude density. Spectral density has a component at FC. If you don't have carrier, then that component will be 0. Because how do you get amplitude? You multiply by small area, then only you will get the some component. At single point there is no carrier. Even though you have some non-zero value at the carrier component, at the carrier frequency, let's say this is my FC and the corresponding point this one, this is some non-zero value. But exactly at FC, exactly at F is equal to FC, what is the magnitude? It is 0. Why? Because it is a density function. Okay, so you can say that there is some energy present in the neighborhood of FC, my carrier frequency, but you cannot say that there is a carrier component at FC. Okay, this is not a carrier component. Okay, you have to understand that. Okay, like we know that. Okay, what does the density function mean? Okay, what do impulse in the density function mean? Suppose if I put an impulse function like this, then it has value. Okay, when we have an impulse in the density function, that means we have a localized component at that frequency. Okay, this is not a localized component. Does not have a localized component. After all, it is a density function, but this guy has a localized component. Okay, and localized component with some finite energy. Okay, or power that we can talk about at that frequency, say FC. Otherwise, when you have a density function which is which doesn't have impulse, and if you want to ask the following question, how much power is carried at that frequency, you put simply like this, and this point FC. If you ask how much power is carried at this FC frequency, then the answer will be 0. Okay, therefore you have to understand that issue very clearly. Okay, so in this there is no carrier component. No carrier component means no impulse. If you don't have any impulse, then you cannot say there is a carrier power explicitly. But you can ask me, there is some value, okay, this value, but that value will not be a carrier. Okay, there is a value of the spectrum at that frequency surely. Okay, it could be 0. Okay, because it is density function. At a single point you cannot say this is the value. Therefore, the process of modulation simplify shifting the spectrum from one location, from 0 location to some other location. Okay, that's all what we have to do. Okay, so that's all we have to do in the case of amplitude modulation. But the drawback of your AM system is there is a power inefficiency. So this is spectrum, not this one, the previous one. Yeah, this is a spectrum. So because of the introduction of the carrier, there is power inefficiency. When the power inefficiency is due to the fact that the carrier component that we have introduced does not carry useful information, I mean message information. You cannot use them, it is entirely useless. Okay, so it is some function to perform now. Okay, carrier component does not convey message or information. That's it. Now you can ask a question, why are we using it still? It doesn't, even though it doesn't convey any information, why do we need this? Okay, because we would be able to recover or demodulate more easily at the receiver. Okay, we don't want the coherent carrier at the receiver. This is one way of looking at it. Okay, one possible answer. Okay, the design of a demodulator, which is extremely simple in this case, which does not even require us to do a synchronous demodulation. Okay, so no need to generate the carrier at the receiver, no phase synchronization, no frequency synchronization, nothing. Very simple, extremely simple demodulator. But in the case of DSBSC, the demodulator is not very simple, it is complex. So for that reason, we go for this AM modulation with carrier. Okay, if I do not require to do synchronous demodulation, I don't have to carry out the carrier recovery process, and that will lead to the receiver very inexpensive, very cheap, very low cost receiver, so that it is affordable for many users. Okay, because I do not require a complicated carrier recovery circuit to produce a local carrier which is perfect in phase and in frequency, I mean synchronous with the received carriers, and that is a real advantage of AM system. So the demodulation can be effected extremely simple by using a very simple circuit which we call something called envelope detector. Envelope detector. This is for double sideband AM with carrier. Okay, so in the previous case we talked about synchronous demodulator, that is for what is that? DSBSC. Okay, so basically we use the fact that envelope E of t, we said E of t is the envelope, right? E of t is proportional to what? M of t, and the recovery of M of t is very simple by a device called a diode. So the demodulation can be done with such a cheap component, very less or inexpensive component, whereas the earlier demodulator, your synchronous demodulator, requires you have to have an analog multiplier, okay, and also locally generating carrier circuit, that means phase locked loop and so on and so forth. Okay, complex carrier recovery circuit. So these are all drawbacks. So these drawbacks can be eliminated if you use carrier in the modulated signal. Okay, so let me stop at this point. In the next lecture we will talk about modulation index or depth of modulation. Okay, or also called depth of modulation, and then we will talk about envelope detection. Okay, envelope detector. So let me stop. Thank you very much.